In the final series of mechanical properties of materials, I have chosen three very important properties. One is the hardness, where I will explain that how we do the qualitative testing as well as the quantitative testing of hardness, and what is the relationship between hardness and strength, which is very important in the design of a system. And then secondly, I will talk about creep, and finally, I will talk about damping. So, these are the three important mechanical properties which we will cover in this final series. So, first let us talk about the hardness. Now, hardness by definition, it is a measure of a material's resilience to localized plastic deformation. Okay. So, for example, a small indentation or a scratch. So, let me repeat. So, it is a measure of material's resistance to localized plastic deformation. Example, a small indentation or a scratch. Now, there are various advantages of hardness testing. First of all, it is a very simple and inexpensive test. You do not need a very special sample preparation. Of course, for micro hardness you will need, which we will talk about it subsequently, but for simple hardness testing no special specimen preparation is needed, and the apparatus is also relatively cheaper. So, one can carry out the hardness testing in a relatively less expensive way. Secondly, it is considered to be a non-destructive method, because you are really making a very small indentation without really affecting the overall sample. And finally, from the hardness test you will not only get the hardness, but also you can get some important informations like say the tensile strength. Okay. So, this is a very important thing, okay, that can be obtained from the hardness data. For example, for metals there is something called a Tabor relationship, okay, in which if you know one of the hardness data in the Brinell scale, the HB data, and then you should be able to actually use that data, and then you can find out the ultimate tensile strength SU using this relationship, where x is n minus 2 and n varies between 2 to 2.7, and this is also known as the Mayer index. So, such this is just an example that how you can further exploit the hardness data and find out certain important properties. Now, hardness generally in an initial stage was used to be actually found out through a very qualitative method, which used to be mostly used by the geologists, and that is based on the ability of one material to scratch another. Okay. So, in that scale the geologists used to consider talc to be the softest material, and its absolute hardness keeping it as 1, then the various materials are used to actually scratch on talc, and that from the depth of indentations and the power of scratching, and then the scratching of one over the other, the ranking used to be done. So, from that scale if you see that from a very low hardness to a high hardness, you are getting something like diamond as the highest hardness 1600. So, that was a kind of course a very qualitative way of determining the hardness. It can only give you an idea of relative hardness one with respect to the other. That suppose you are taking two materials and you are able to scratch material B with the help of material A, and that would signify that the hardness of material A is more than the hardness of material B. So, that was a very qualitative method in the Mohs scale. At a later stage, the quantitative hardness tests started to get evolved, and then there are basically two classifications of them. One is called the macro hardness test, where as I told you that not much of sample preparation is needed, and the other group is called the micro hardness test. Now, in the macro hardness test there are many, but we have chosen Rockwell hardness test, Brinell hardness test and Vickers hardness test, and in the micro hardness test the Knoop micro hardness test and Vickers micro hardness test. So, total these are the 5 experiments that actually one can carry out in order to find out quantitatively the value of hardness. So, the first one is the Rockwell hardness test. Now, the basic principle, as I told you, that resistance to plastic deformation, that is same in all the cases. So, the only thing is that what kind of a indenter that you are using in terms of like this indenter, if you look at it, the geometry of the indenter, that actually varies from test to test. So, when we talk about a Rockwell hardness test, first of all, Rockwell hardness test employs 2 different loads. One is a minor load, okay, it is first applied for good contact between the indenter and the sample surface, and this followed by a major load, and the depth of indentation is recorded on a dial gauge after removing the major load. Now, here the indenter is actually cone shaped indenter, which is usually used for hardened materials and sometimes for steel ball for relatively less hard materials. And so, the sequence, if you look at it, that you first apply the minor load and then you apply the minor plus the major load, and then you withdraw the major load. So, you have the minor load and then withdraw all of them and then measure the depth of penetration. Now, suppose you know what is the permanent increase in the depth of penetration due to major load. Okay. So, once you know that, and then there is a constant E which depends on the form of indenter. Okay. So, for example, if you use diamond indenter, this is about 100, if you use steel ball indenter is about 130. So, then you can get HR, Rockwell hardness number, by actually simply subtracting this small e from capital E. So, that is how you can get it. Now, in the HRA scale, there are 3 scales of Rockwell scale. One is scale A, which is known as HRA, and there the indenter is cone shaped indenter. The load is usually 60 kg. It is used for carbides and ceramics. So, that means it is used mostly for ceramics type of systems. Then the B scale of Rockwell, HRB, where we use the steel ball indenter. The load is more here, about 100 kg to create plastic deformation, and then the typical material is used in the non-ferrous metals, it is used. And then C is used mostly for steel. So, HRC scale, and then once again we use a cone shape, 150 kg load is used for ferrous metals and tool steels. So, that is the Rockwell hardness test, okay, and this is a typical Rockwell hardness machine that you can see here. That is a Rockwell hardness machine. Now, the other one that is also very popular is called the Brinell hardness test, and this is used for also testing metals and non-metals of low to medium hardness. Okay. So, Rockwell hardness you include the ceramics also, whereas in this case it is mostly for metals and non-metals of low to medium hardness. Now, in this case, however, the indentation is done not by a cone, but by a hardened steel ball, as you can see it here, that by a hardened steel ball, okay, or sometimes it is cemented carbide ball of 10 millimeter diameter is generally capital D, that is what is generally conventionally used, which is pressed into the surface of specimen using a load P of either this load varies, either 500 kg or 1500 or 3000 kg for a specified time, and the time is generally between 10 to 30 seconds, minimum 10 seconds up to 30 seconds. Now, you know which load you are using, you know what is the diameter you are using, and then all you have to do is that you have to find out this mean indentation diameter. That means, you get the indented shape and you calculate these diameter at 2 different points D1 and D2, and then take an average of it. So, that is what is our D, and once you know D, you can use this formulation to find out the HB. And there is a thumb rule here, and that is the tensile strength can be actually calculated directly as 3.45 times Hb, and that is usually used for steel alloys. But as I told you earlier itself, couple of slides before, if you remember, that generally a more generalized relationship is actually this one, which is used in terms of finding out the what you call the strength for various types of materials. So, this is not very material specific. Okay. Now, we come to the Vickers hardness test. Okay. Here, what is the difference? Unlike these Brinell hardness test, the shape is different here, as you can see that it is a square base diamond pyramid indenter, and which is generally having an angle of 136 degree is between the opposite faces. That is what is used in the Vickers hardness test. Okay. And in this case, the hardness is obtained by dividing the load, which is generally 1 to 120 kg, with the surface area of the indentation. And the surface area is calculated from the diagonals of the length of the impression. So, here the impression is actually something like in this case it is a square type of an indentation, unlike the circular indentation that you have seen for the Brinell case. So, you once you know this indentation size, okay, then you know that, and you know the force that you are applying. So, 1.854 times that, and F is the applied load in kg, then you will be able to get the Vickers hardness test. So, that is how these three tests are used in terms of finding out the quantified value of the hardness data. Now, sometimes what happens is that this hardness is insufficient, particularly when you will see that you make a very thin layer. Okay. So, this kind of general hardness is good for when you have a single material, but many a times what happens is that we give a special surface coating on metals. Okay. Let us say we talk, when we actually work on things like suppose gears. Okay. So, these are the suppose the faces of the gears, and which works against another gear. Okay. So, a smaller gear. Now, so there is a continuous contact between the two. So, in this kind of surfaces, you must give a special coating, okay, on the cutting on the teeth of the gear. So, you give a special very thin coating layer, which is very hard, so that to save it from wear and tear. Now, this kind of very thin coating layers you cannot really see that how you cannot really use the macro hardness tests for doing that. You need a micro hardness test for doing it. So, for such cases the micro hardness test comes into picture, and the important thing here that the load applied here is much smaller, because the indentation thickness is very low. Okay. Indentation itself is very small, and sample preparation is definitely needed. Okay. So, there are two methods that is used, Knoop hardness and Vickers micro hardness. Let us go to each one of them. So, in the Vickers micro hardness test, I mean the Knoop hardness test, it is mostly used for very brittle materials or thin sheets. Okay. So, here you use a pyramidal diamond point, okay, which is pressed into the polished surface of the test material for a specified dwell time, and the resulting indentation is measured now using a microscope. Okay. So, the length to width ratio of the pyramid is maintained as 7:1. Okay. And then you can actually find out the Knoop hardness value, where F is the load in kg and L is the long diagonal of the impression. So, you can use this relationship in order to get the Knoop hardness value. So, that is, as you can see here, that the load here that is used, F is the load in kg. Now, that load is substantially smaller in comparison to the macro hardness tests. The other one is actually Vickers micro hardness test. Here also you can see that the load range is like 100 grams, okay, 1 to 100 grams. So, that is the kind of a thing we are talking about when we talk about micro hardness tests. Now, this slide gives us a kind of a very broad picture of two things. One is that suppose I work with something like a Brinell hardness, okay, then I can actually compare that what will be the performance of the same material in terms of Rockwell hardness, or I can compare it in terms of Noof hardness, etc., or even with the Mohs hardness. And the other thing is also this is telling us is that what is the general range of hardness that we can expect, because the material science has advanced so much that most of them are fairly standardized now. So, for example, when you talk about the nitride steels, so somewhere between 1000 to 2000, maybe 1200 or 1300 is the maximum value you can see, and in the Brinell hardness scale. For the cutting tool, it is somewhere like, as you can see, maximum value of 700, around that range. Okay. And similarly, for all other materials, like for brushes, as you can see that it is somewhere like 70 or so in the Brinell hardness. So, this particular slide tells us that where do we expect the values to come from, that has been standardized. The other thing also, that the formulation that I told you, which is used for the calculation of the yield strength, in this table, which is from the Ashby and Jones book, you can actually get this directly, this yield strength. For example, you get some value like 1200, and you go through this, you get an yield strength of something like 4000 MPa. So, corresponding to each such values in the hardness testing machine, you can get an approximate yield strength value. So, that is the good part of this kind of a handy table. Okay. So, we have talked about the hardness. Next, let us come to another important property, that is what is called the creep. Okay. Now, many of you might have experienced creep as a day to day experience. For example, you use the nylon wear for outdoor garments drying, right, and you will see that you put a fixed tension, you fix your nylon wears, and then you put your garments day 1, and after a month or so you see that this whole thing is actually slacking, and it is coming down more and more, it is getting loose. So, why is this happening? This happens because under a continuous load, every material starts to get a permanent deformation over a period of time, which is known as creep. Now, creep has a very high temperature dependency. Naturally, if the temperature is more, then what will happen is that there will be, as you are going closer to the melting point, you are getting a flow like behavior. So, under loading, this effect of this permanent deformation will be much more. And a creep test generally involves a tensile specimen. Once again, in you can use a universal testing machine under a constant load maintained and under a constant temperature. So, that temperature is important, because as the temperature increases, the same stress level can actually create much more deformation in the system. Now, this is a very important test, because its application is there in terms of, suppose, turbine blades which work at a very high temperature level, or nuclear reactor components, jet engines, heat exchangers. So, those applications where there is a stress or mechanical loading at elevated temperature, creep is must. Okay. So, that is what is the importance of the creep test. Now, creep generally occurs in 3 stages. Okay. So, the first one is the primary stage, which is for a smaller duration, mostly transient, and then there is a longer period which is known as the secondary stage, and the creep rate is more or less steady in such a case. Okay. So, you can get a slope, a continuous slope more or less at this stage, okay, and you can predict that how much it will be creeping in that time period. Then there is a tertiary stage. Okay. So, that is as you can see here, that with respect to time, beyond a particular time, the creep increases actually exponentially, as you can see in this picture. So, that is that actually goes towards the failure. Now, at temperature, I told you that less than 0.4 of the melting point temperature, generally after the initial deformation, the strain is virtually independent of time. But with the increase in stress or temperature, the creep strain increases and the rupture life increases rapidly. Now, to do all these things, we use mnemonic 75. This is a EU, actually European Union standard, as the creep reference material. So, any new material you want to test, you test it with respect to mnemonics. These mnemonics are basically nickel based super alloys, okay, and they contain about 50% of nickel and 20% on chromium, with some additives such as titanium and aluminum. So, with respect to this reference, you can actually measure that what is the creep that is happening to the system. Now, here you can see that when the temperature is less than 0.4 Tm, the creep is not so predominant. Okay. The creep strain is almost constant, but if the temperature increases, okay, or stress increases, you can see how the nature is changing. Okay. That means there is a steady increase of the creep strain. So, that is something that is that needs to be always studied with respect to a material. And there is I will not go into the details at this moment, but there are various mechanical models that are used actually. A very common model is something like a spring, okay, a material model and a dashpot combination in series. Okay. So, and the load is coming here. Okay. So, this is a spring K and this is a dashpot. Okay. So, imagine that you are applying a load F and how this system will be behaving. Okay. So, that is something that approximately kind of simulates the creep behavior of a system. Okay. Finally, I will talk about damping, okay, which is very important, because as you know that many mechanical systems undergoes dynamic loading, okay, and also civil structures like which undergoes dynamic loading because of different reasons like wind loading or earthquake or maybe vehicles moving, transport load, etc. So, vibration is ubiquitous. Now, there must be a material property which actually determines that what is the level of vibration, or what is the kind of energy dissipation possible in the system. Now, this method of vibration reduction actually there are two ways. One is the damping capacity and another is through the stiffness. Damping specifically refers to the dissipation of energy from a vibrating system. So, it is mostly the damping that is important, particularly during the resonance of a system. That means, when the natural frequency matches with the excitation frequency, it is the damping which creates the predominant role. So, the damping study is very important, and that helps in terms of shock absorption, fatigue failure prevention, noise reduction, etc. So, this is typically an under damped curve, as you can see, and this is actually under viscous damping, and you can see that the response is coming down exponentially. Okay. So, as the damping increases, this actually will be more and more, and there is something we call the settling time. That means, in comparison to the initial value plus minus about 2 to 5%, when the amplitude the initial amplitude comes down to within say 2 to 5% level, we say that the vibration has actually damped down. So, there are various ways in which we can actually quantify the damping. Now, there are two important types of damping. One is called the viscous damping, and as you can see that like a seismic protection or in any door, you will see that the door closer is actually a dashpot. Okay. So, this dashpot is having actually a piston and a cylinder combination, and the damping force here is considered to be proportional to the velocity across the damper and acting in the direction opposite to that of the velocity. So, if the direction of force is this way, okay, and then the opposing force damping is coming as an opposing force. Okay. It is opposing the direction of the velocity. Okay. And so, this is very important in terms of viscous damping model. There is another type of a damping model also, that is known as the Coulomb damping model. So, which is basically dry friction force between two solid interfaces. Now, in this model, the magnitude of damping force, unlike the last case where it is proportional to velocity, which means higher the velocity more is the resistance. In this case, the damping force is assumed to be constant, and that is, it is independent of the relative velocity, unlike the last case. However, what happens is that there is a signum function that governs. Okay. So, the signum function is positive for positive velocity and negative for negative velocity. Okay. So, that is how the damping force will change its direction, change its sign. So, that is for the Coulomb damping. So, these are the two very important dampings, viscous damping and Coulomb damping. Now, how material properties are related to it? Okay. One important thing here is that what is the damping ratio, and damping ratio is basically the ratio of damping constant to the critical damping of a system. Suppose we consider a single degree of freedom system, something like, like if we can draw it, a single degree of freedom system, something like a stiff spring here, a damper or a dashpot here, and a mass M. Okay. So, this is called a single degree of freedom system. It can actually move only in one direction. Okay. So, in such a case, the damping ratio zeta is actually the ratio of C over Cc, where Cc is the critical damping called 2 root Km. And thus, for critically damped system, the value of zeta is actually unity, because C equals to Cc, whereas for under damped systems zeta is much less than unity. Like as you can see here, that this is the case of a critically damped system, and all these where the oscillations are actually continuing are the cases, these are the cases of under damped system. So, this is under damped, okay, under damped system, and this is the one single case that is shown where zeta value is greater than unity. This is the over damped case, which is not generally, you will not see that practically. Most of the cases it is actually under damped case, and it is of importance that what will be the value of the zeta at that corresponding to that under damped case. In fact, the quality factor Q also actually determines the degree of under damping, and which is typically the ratio of the bandwidth to the central frequency of the system. In the next slide, I will just show you that how the damping changes the response of a system. So, if you just look at this, that there are two systems I have shown here. One is, this is a system which is like a system which has a damper. It is like a damper which is in the form of a copper block here, which actually converts the oscillatory motion. Inside the copper block there are actually magnetic blocks there, and the magnetic blocks gets actually as it moves inside the copper block, it actually generates the eddy current, and thus the vibration is converted to electrical energy in the copper block. So, that is kind of a damper. Okay. And then there is this situation where there is no damper, because there is, you can see there is no copper block there, and hence even if there are these magnets here, as you can see, these magnets actually has to create an electric field in order to create damping. Now, let us see that how such a system would actually behave in terms of if you can see in terms of the oscillations. Look at the right hand side and see that how vigorous is the oscillation. If you look at the top plate, okay, and you can also see it in the oscilloscope. And if you look at the left hand side, you would see that most of the vibrating energy is getting transferred to electrical energy, and hence you get much less vibration amplitude in the left hand side case. So, that is typically what you will see in the case of a say system which has a damper in it. In this case, the specific damper is called a eddy current damper, and the frequency is of damping is around 8 hertz. Okay. So, it is between 7 to 8 hertz level you would see it. As you increase the frequency, you may come across a situation where this will be even more vigorous here. Okay. And on the other hand, you will see that with the damper there will be hardly any as I told you that the damping is very important close to the resonance. So, hence whenever you will come across the resonance, you will see that the damping becomes, you see there is a sudden decrease in the whole system. So, that is kind of an example that how with and without damping typically a system would behave. Okay. Now, let us go back to the quantification of the damping. So, while quantifying the damping, we have to talk about another very important factor which is known as the loss factor. Okay. And the loss factor is actually defined in terms of the ratio of the energy dissipated from the system to the energy stored in the system for every oscillation. So, that means if you consider that there is a underdamped situation, that means with respect to time, if you plot the response, then the response is in a cyclic manner. Then at however, the amplitude is coming down gradually. So, you find out that for one particular cycle, okay, so let us say from this point to this point, okay, you have to find out what is the ratio of the energy dissipated from the system and what is the energy stored in the system. So, that gives you the loss factor eta, and that is a material property, and this eta is actually related to both the quality factor and the zeta by this particular relationship. Okay. So, even though zeta and form factor q are not directly the material property, but eta is a material property, because the more there is hysteresis, for example, in the material, the more will be this kind of energy dissipation. And this actually some material, for example, aluminum, you will see that the loss factor is much smaller in comparison to steel. So, which means steel dissipates more energy inside it. And if you look at rubbers, which are generally used as damping materials, they have a much higher, right, like an order of magnitude higher of the loss factor. So, that says that why we use rubber or neoprenes etc. as damping material, unlike the metals. Generally polymers have much larger energy dissipation, and hence the eta is much more for the polymers. So, that is broadly the mechanical properties that we have discussed. In the next lecture, we will now leave the mechanical properties. We will try to find out what is the source, what is the reason of these mechanical properties, and we will start that with the atomic bonding. Okay. So, we will go to the very core issue of atomic bonding, and we will see things like the ionic bond, covalent bond, metallic bond, hydrogen bond, and van der Waals bonds. So, that once we understand some of these properties, we will be able to explain with the help of the atomic bonding. Thank you.